All right, welcome back. We are going to go through the last part of topic 3. We're going to look at p-values, test statistics, H0, the null hypothesis, and the alternative hypothesis. We're going to look at power of a statistical test, type 1 and 2 errors, and also the effect and how we measure each of those. All right, so let's get started. Okay, remember that the p-value measures the probability that the null hypothesis is true. So we calculate the p-value for our particular experiment, our particular sample. And we do this in a test statistic. A test statistic tells us what the p-value is. It tells us the z-score, which we can then translate into the p-value score. Okay, so test statistic is where we get the z-score and the p-value score. So a test statistic is a test to work out whether our statistics are useful or not. Now, when we choose our test statistics, our variables, we look at the nature of the relationships between the variables, the statistical distribution of the population, very importantly, the size of the sample, and parametric requirements that we assume in the test. Okay. Now, the p-value constant that we measure our results against, this is called the alpha. And it's depicted by the Greek letter alpha. Okay. The alpha value is the significance level. It's the cutoff p-value. Okay. So this is normally by convention 0.05, which is 5%, or 0.01, which is 1%. The alpha value specifies the maximum risk we are willing to take of making an error if we reject the null hypothesis. So it measures the risk we make of accidentally thinking that there is a significant result for our research when there isn't. Okay. Now, when we get our p-value, it needs to be within the parameters of the alpha value. In other words, it needs to be less than the alpha value. If it's equal to or greater than the alpha value, then we take the null hypothesis as not rejected. In other words, our experiment hasn't succeeded in showing any significant change in the variable. The change is probably due to chance, it could be due to a mistake, it could be due to our sample size being too small. Okay. Now, when we speak about the null hypothesis, we always say either rejecting the null hypothesis, which means that our alternative hypothesis is can be taken as accepted and as supported by the research, or not rejected, meaning we can't rule out chance or an error as being the cause of our results. Okay. But even if we got exactly the result we expected, we can't completely rule out chance. We're just saying that there's an acceptable level of risk that we could be wrong. Okay. Now, when you're talking about your alternative hypothesis, you can say that you accept it or that you reject it, whereas the null hypothesis, you can only say rejected or not rejected. If the null hypothesis is not rejected, we can say that the research hypothesis could not be confirmed. Okay, let's look at type 1 and 2 errors. Okay, this can be a little bit befuddling. I remember it as follows. H0, HO, true, is type 1. Okay, so if H0 is true, we do risk making a type 1 error, which is when we would assume that the H0, the null hypothesis, is false. In other words, that our alternative hypothesis is probably true and that we have found a significant result. But the truth is that our H0 hypothesis is true. A type 2 error is when the H0, the null hypothesis, is false. In other words, we've decided the null hypothesis is true and we're wrong. It's false. So I remember this as hof to, meaning go to court. So I remember hot one, hof to. Attractive person goes to court. You can make up your own mnemonic, but this is something to just put into memory and hold it there until after the exam at least. Ideally forever, of course. Okay, so now we've got the alpha. Okay, here we go. If the p-value, oh my gosh, this is, when we type 1 errors relate to the alpha, okay? So when the null hypothesis is true, we've made a mistake because our alpha value has not picked that up correctly. It is true that the null hypothesis is actually the case, that there's no change, that there's no connection. Our experiment is seeing an effect that it's not actually there. And that may be because our alpha value is too high and it allows for too great an amount of random error or too many mistakes or other variability in the data, okay? And we've got another term here, we've got beta. Okay, beta is a measure of the type 2 errors, the failure to reject a null hypothesis that is really false. Alpha value we can make quite precise because we set that. And also because that correlates to the null hypothesis goes with the equal sign, remember? So it's very precise. But the alternative hypothesis is about a range. So we can't pin that beta value down exactly. Now, if we are right that the null hypothesis should be rejected and we reject it, then we have a test that has statistical power. In other words, it's sensitive enough to pick up a real result in the numbers. And the power of a test is calculated by subtracting the probability of a type 2 error from 1. In other words, power equals 1 minus beta. So it's an inverse relationship. Okay. And it would always add up to 1. So that may be familiar to you from alternative complements in probability, which always add up to 1. Now, we can increase the power of a test even if we can't calculate the value of 1 minus beta. There's 4 things mentioned here. Number 1, most importantly, I think, increase the sample size. Number 2, decrease errors. They mention 3 errors here. Sampling error, measurement error, or external variables. Third way is there's three. Sample size, error, and choice of statistical test. So parametrical statistical tests are better than non-parametric techniques, so we prefer to use them. And we'll see more about what kinds of tests there are as we go through the book. Okay, effect size. Okay, remember the law of large numbers. The larger the sample, the more accurate the information. The closer the measurements match up to the theoretical amount expected, the expected value. Okay. So say we're looking at UNISA students, we measure their IQ and we find, oh, it's 102. The mean of their IQ is 102. Look at the difference sampling size makes. It could lead you to a Z value of 0.4, which is very high, and a p-value of 0.337, which is again very high. And far too high to be statistically significant. That could be one clever student could pull that whole thing skew. 100, for a small difference such as X bar is 102, that gives us quite a high Z score of 1.33 and a p-value of 0.092, which is nearly double the alpha value, which is 0.05, right? But now look what happens if we have 1,000 students. Oh, sorry, I've got my Z score is now high instead of low. Okay, so Z score and p-value are inverse. The lower the Z score, the higher the p-value. So the Z score here is very high, but the p-value is approaching 0. Now, the convention of having those that 0.000 means that there are numbers that come after. It's just that we've rounded it to the nearest 10,000. Okay. So now it's not just about getting a test that shows that there's a difference. There's also, we've got to think about, does it matter? You know, a difference of 2 IQ points doesn't really matter. It's virtually non-meaningful. Okay. So now we have to look at the effect size. The effect size is the question of how important is this result? How much does it change the world and the effect of one variable on another? That change, what effect is that? How big of an impact is that? Okay, so there's a little formula for effect size, and it's represented by the letter D. We take the difference in the two means, which in our first experiment was 4, remember? 104 minus 100. Our second experiment with IQs at UNISA, it was 102 minus 100. So it would be 2 or 4 over the top, over the standard deviation. So in the first experiment, we'd say 4 over 15 being the standard deviation for population IQ. And that would give us D, an effect size of 0.267. Now, what's nice is that we've got a nice intuitive scale for the D, the effect size. Around 0.2 is small, around 0.5 is medium, and around 0.8 is large. So that's really nice and easy to remember. Effect size, power, and sample size are interrelated. You can determine one if you have information regarding the other two. So if you know your desired effect size and you know the power of the test, you can then decide and measure and calculate what sample size you need in order to do your statistical research. Okay, here is a summary of topic 3. So go through this very carefully and make sure that you know all of this. I don't want to go into detail because we'll get bogged down. It'll get overwhelming quickly. After that, there's a whole bunch of exercises. And if you've done topic 1, 2, and 3, you're ready for assessment 1. Wishing you lots of luck and seeing you in the next video. Okay.